Hey everybody, in this video I'm going to be answering this exponential growth word problem. So with exponential growth, there's this formula. There's lots of different versions of the formula in general, but the one that I always remember the most is from finance. It's the continuous exponential growth model, which is A equals P times e to the power of RT. Now you'll see other things in your book and in the videos. You might see P of t is equal to P sub 0 times e to the power of kt. And notice that it's very similar, right? We're just using function notation right here. And then the P sub 0 instead of a regular P, but they really mean the same thing. What they stand for is the initial amount, whatever your starting amount is. Then E is the natural number E, and then the power always has a growth factor, and then T, which is the variable that you would be plugging in to find a future value. And then the future value is A or P of T, or it could be other symbols. So there's lots of different ones, but they all kind of amount to this. If it has E involved in it, it's going to have some multiplier in the very front that is going to represent whatever amount of the substance is that you started with when time was equal to 0, right? That's why you have a subscript on this one saying P sub 0, meaning at time of 0, what was the starting amount? Then E, the natural number, then R or K, those represent the growth rate or sometimes a decay rate. And so if it's something that's going to grow, like suppose you invest money into a savings account where you get a certain percentage of interest, then it's going to be growing and your growth rate or your R percentage or your K would be positive. But if it was something that was going to be decreasing over time, then you would see a negative growth factor. So I usually just remember A equals P times e to the RT, right? So A is your annuity or your future value. So annuity, if you're talking about money in general for any substance that follows linear growth, A equals the future value, and P is the initial amount at time of 0. So the starting amount of your substance. It's also called P because in finance it's called the principal, the amount that you start with. Then R would be the rate. So this could be the rate of interest. This could be growth rate. It could be decay. And remember that it'll be positive when it's growth and negative when it's decay. And then T is, when it comes to finance, it's usually time in years, but it doesn't always have to be years. So you can use it in any context, but just make note of whatever the units are. So we'll just leave it time in general and just say, this could be years, it could be seconds, it could be minutes, it could be hours, just depending on the problem and the way it's set up. All right, so when I read this problem, it says the count in a bacteria culture was 400 after 10 minutes and 1700 after 35 minutes. Assuming the count grows exponentially, what was the initial size of the culture? So because we've been told that the count of the bacteria grows exponentially, we know we can use this as a basic model. All right. Now, the next part says, what was the initial size of the culture? So in other words, we want to solve for P, the initial amount. Now, in order to solve for a single unknown in an equation, if you have just one equation, you can only have one unknown if you want to find out what it equals. So we need to make sure to replace all the other variables involved here. We need to find a future value and a corresponding time to go into the A and the T, we also need a growth factor. So we need a rate of, in this case, it's bacteria, so it will be growth, not decay. So it'll be a positive R value. All right, now R or K or whatever letter you're using to represent your growth rate is going to be usually between 0 and 1, and either positive or negative. Again, positive if it's growth and negative if it's decay. So let's see what other information we were given and what we can do with it here. So if we think of ordered pairs in the form of, let's say, time, which here the unit of time being discussed is minutes, right? So we'll say minutes for time, and then the bacteria population is going to be the other corresponding value. Okay, so that'll be T and A. All right, so first we were given 10 minutes with a count of 400 bacteria. Then we were also given 1735 minutes. So 35 minutes, whoops, 35 minutes and 1700 bacteria count. So what we can do is take our general model and replace the A and the T, and we'll do it twice, and that'll give us two equations. It'll give us a system of equations that we can use to solve for P. So let's go ahead and put this all together. So first of all, I'm going to say A is equal to P E R T, and I can replace, using the first pair, I can replace the A with 400 and then the E with, or I'm sorry, the T with 10. Then I can do the other pair, 1700 equals PER times 35, right? And notice that in both of these equations, we have replaced all of the variables except for P and R. So there's two unknowns. Remember, E is not an unknown. E is the natural number. But P and R are both unknown right now. And when you have two unknowns, you need two equations to solve a system in order to come up with those values. That's how I knew I needed to use these two ordered pairs to make two separate equations with the same variables in them. So now that I have that, what I can do is solve both of them for P. So I'm going to rewrite this. P equals 400 divided by E to the 10R, and P equals 1700 divided by E to the 35R. Okay, so see what I did there is I took each equation individually and divided both sides by E to the R times whatever the number was. So I have P isolated for both of the two equations. And now I can notice that P and P are equal. You know, P is equal to this, but equivalently, P is equal to this. So these are two separate expressions that are both going to be equal to the same amount, which is our principal starting amount that we're looking for. So because I have those two that are equivalent, I can set them equal to each other. So I can just go 400 divided by E to the power of 10R is equal to 1700 divided by E to the power of 35R. And now I want to solve for R. So solve for R. Okay. Now to solve for R, I'm going to cross multiply because um, if I want to get e to the 10r out of the denominator here, right, I'd have to multiply that on both sides. And if I want to get e to the 35r out of this denominator on the right, I would have to multiply by e to the 35r to cancel that off. But to keep things balanced, I would have to also do it over here. So as you can see, what ends up happening is I have 400 times e to the 35r. If I were to cross multiply, that's a shortcut instead of doing both steps separately. So we get 400 times e to the 35r is equal to 1700 times e to the 10r. Now, I want to get my e's together, so I'm going to divide both sides by e to the 10r. And then I'm also going to want to get my two numbers together, so I'm going to also divide both sides by 400. So that'll cancel there. And so now what I have is e to the 35 over e to the 10r is equal to 17 over 4 because the zeros cancel out. You can think of it as 17 times 100 over 4 times 100, and the hundreds cancel. Okay, so now I have this. And because I have the base of e on top and bottom, I can subtract, keep the base the same and subtract the exponents, right? So you guys know this because you've done something like x to the fifth power over x squared is x to the third, right? Because 5 minus 2 is 3. So we're just applying that exponent property here with the two exponents of e that are in like terms, so I can combine them by subtracting. All right, so now that means that now I have e to the power of 25r equals 17 over 4. And now I have something that I can take the natural log of both sides to solve for r. But I want to back up a step and say this was a lot of stuff going on that we just did here. And I want to show you something that is a big shortcut. So let's just back up here. Let's go back to where we had this set up. And instead of doing all that other stuff that we did, we're going to get rid of this. You can still do it, but you're going to see that what I'm about to show you is a lot simpler. So I'm just getting rid of some things here. Okay. So if this ratio is equal to this ratio, the interesting thing is that the ratio of these two and the ratio of these two should be equivalent. So in other words, if I were to kind of think about just rotating this 180 degrees this way, let me get my pen to kind of show you this way, right? We want to not 180 degrees, but 90 degrees, just turn it sideways so that I had 1700 over 400 is equal to e to the 35r over e to the 10r. Then we would end up with that same expression, or same equation rather, of 35 minus 10r, 17 over 4. Yeah, so we would have ended up at that same exact equation. E to the 25r is equal to 17 over 4. So, you know, proportion, when you set up a proportion, you're showing relationships that are equivalent, right? And it works vertically and it also works horizontally. So that's why I was able to put the 1700 over 400 and the e to the 35r over e to the 10r because these are ratio relationships that are equivalent. And it works that way, as you can see. A lot easier than doing all the cross multiplying and all that other stuff. So let me um, just pick up from this last line here. Just bring that up with us here and proceed. Okay, so now we're ready to solve for R. And to do that, R is right now in the exponential position. So I want to get it down to ground level. And to release it from that exponent position, I'm going to cancel out the base of E. Now, how we cancel out the base of an exponential expression is by taking the natural log, which is log base E. Okay, so the natural log of E. And then I have to do the same thing to both sides as always, right? And because the base of the log and the base of the exponential expression are the same, this cancels out to 1. So this is a property of logarithms that I'm applying here. I'm just going to put it over on the side here. The log base b of b is always equal to 1, and that's because if you were to take any base and raise it to the power of 1, it would equal b, right? So this is like saying natural log is the same thing as saying log base e. And then if I'm saying of e to the 25r, I can also apply this, the log base b of c to the a is equal to a times the log base b of c. So in other words, you can put the logarithm, or I'm sorry, the exponent as a multiplier in front of the logarithm. So I'm also applying that here in the next step. So then I have, in the next step, I would have 25 times, 25r rather, times the natural log of e. And the natural log of e is just 1. Then over here, I still have natural log of 17 over 4. And so finally, we get 25r equals natural log of 17 over 4, which means that now I can divide both sides by 25 to get r alone. And then I'm going to want to hold on to whatever that value is. Now, when I do it in my calculator, I'm just going to show you a picture of the calculator that I like to use. This is the TI-30X2S. And what you would do now is you would hit natural log, which is right here. Okay, natural log, the ln key. So I'm going to do natural log of 17 over 4 divided by 25. So I'd literally do the ln key. Maybe I should use this. ln key. And then you're going to see it come up with a set of parentheses. So then you're going to put in the 17 divided by 4. And then you need to close the parentheses. Then you're going to divide that by 25. And what you should get, so let me see what I get when I do it on mine here. You can't see what I'm doing. It comes out to approximately 0.057876,759. Now, to maintain accuracy, we should really understand that this number keeps on going. This is just the digits that show up on my screen, but there's more. And yes, we could round it and maybe it would be fine, but we don't really want to round it because remember, we're going to be using this number in other parts of the question. This is our growth rate, okay? This is R, and R is going to be in our model here, right? So we're going to come back to where we started and set up our exponential growth model and put the R there, the value of R there. And we don't want to round it. Okay, so if we can be smart, which we can because of technology, the smarter thing to do is either to keep it all written out just like this, which means we would take our model and say, okay, A is equal to the principal times e to the power of r, which is the natural log of 17 over 4 divided by 25 times t. Okay, so that's how we would write it if we wanted to keep everything exact. Now, a cooler and easier way to do this, instead of having to type all of that, is we can store this into, so whatever this value is in your calculator, if you're using the model I'm using, you can use the store key. Okay, it's the store button. And that, let's go ahead and highlight it, is right here on your calculator on the TI-30X2S, right? So when I do that, what comes up when I hit that key is, this is what I see. I see an arrow in the screen and then A, B, C, D, E, and then you can keep going to the right to find more letters. So you can select any one of these and then press enter, the equals key down at the bottom. And so if I chose A, I would be saving R into A. So instead of having all this to write, I can just write A to for myself. Like once I store it into A in my calculator, then I can just rewrite this as A for myself so that I will know how to calculate it whenever I want to use this function for other parts of the question. So that's what we're going to do. I also want you to note that this is a positive growth rate between 0 and 1. As I was expecting, it's between 0 and 1, and it's positive as I was expecting because this is a growth problem. It's bacteria growth rather than decay. If it had been a decay problem, it would have been a negative. So I'm happy to see that it was positive. And now, I don't know if I would store it in A because we have an A in our formula. I might instead use B just to keep myself from getting confused because there is another variable there. So then I would have just selected, used the arrow key right here to move over and select the B instead. Or another option is you could just start calling A, instead of saying A, you could start calling it Y equals, you know, and then you wouldn't have to worry if you were using the letter A. But in any case, I'm going to keep it like this. I'm just going to keep it A equals because I already set everything up that way. So I'm going to set it up as A equals, and then I'm going to use B as my exponent growth rate. Right, so now my model is, I'm going to come back in here and just replace the R with the letter B to represent the variable that I stored it into in my calculator. And then we can go on to the next part of the problem. So just to show you, here's the problem again, and there's the answer that we're looking for. Now notice we're not there yet. We're about to find out what P is, but all we've done so far is figured out what R is. The growth rate. So to find P, we have another step. And what we're going to do is use one of those ordered pairs again, so we can come back to one of the equations we started out with in our system over here, right? We can just use one of those. So let's use the 400 equals P e to the R, which we know is stored in B, and times 10. So I'm going to write it as 10B. Okay, now to solve for P, I would just divide both sides by e to the 10B. And I really could have taken that from here, right? I already had it solved for P. I forgot. I didn't even look at that. Yeah, so I didn't have to solve it again. I already had it like that. So all we would really need to do here is calculate this in the calculator. So once again, we would be going to the calculator and we would do P equals, use a different color, P, which is what our answer to whatever we calculate is going to be our P, is equal to E, wait, what did I just say? I said 400, right? 400 divided by E to the BT. Or no, 10B, right? 10B. Because it was 10 times R, right? 10R, so 10B, because R is my B. And then I'm just going to literally put that into my calculator. So I'm going to type in 400 divided by, then I'm going to go to my second, I'm going to use the second button. Use a different color here. Use the second key to get to my E that's above the LN key. And I'm going to do 400 divided by E. It's going to come up as E and then this and then a set of parentheses. Then I'm going to type in 10. Then I'm going to go into my memory variable and select B. Okay, so the memory variable is right above the store key. So now I'm talking about this one right here, memvar, MEMVAR. I know it's a little hard to see. I can show you one maybe over here. I had another picture of it. Is that any better? I can't really zoom in on that. Let's try this one over here. Can't really zoom in on that. So I wish I had, well, that kind of, you can kind of see it better there. I guess not really. Anyways, it's a little hard to show you without, an emulator, but that's where it is. It's the third button up from the bottom on the left-hand side. And then when you pull that up, you're going to have the choice of one of these variables again, and you're actually using it in your calculation. And so when you do that, so let me just make sure I have what I'm supposed to have here. So the natural log of 17 divided by 4, and then quantity divided by 25 was equal to 0.057876759, and then I stored it into my B variable. And now I'm going to do 400 divided by E to the power of 10 memvar B. Enter. And then I get it's approximately 224.2355258. And again, I'm going to replace P in my function so that I can use it to answer other parts of my question. So I'm actually going to save that into a variable as well, and I'll call that one C. I don't have any real reason for using C. It just feels like the next correct thing to do. So I used B and now I'm using C. And so my function now, I can replace the P here with just C. And that means from my calculator. All right, so now I can go on and answer other parts of the question. So I've already answered the principal. I have my function now that I can go on and answer what is the doubling period. Well, a period is a period of time. And so we know we're looking for a t-value, time in minutes. And Doubling time means whenever your initial amount would become double, or whenever a certain amount, however many minutes it's going to take for that certain amount to double. So what we do, you can think about it like this. Since we know that our principal is 224.235 and so on, if you were to double that, that would be 448.46 and so on. Um, that's going to be really hard to double. But if you thought about putting twice that amount in place of A, then you could solve for T. But what happens is, and I'm going to use a simpler model so you can understand a more a shortcut really. Let's pretend, here's another example. Other example that's more simple, okay? Let's say we had A equals P, which was a starting amount of 10, times P, oh, sorry, that's not what I meant to do, times E to the power of, um, let's say it was a 5% growth rate, 0.05t. And the question said find the doubling time. That would mean that I would set the future value to 2 times 10, which would be double the principal, right? And then I would solve for t and figure out how many minutes it took to do that. So this simplifies to 20 equals 10 e to the 0.05t. And then what would be my next step in solving for t is I would want to divide by 10 on both sides to cancel this out. And then what would 20 divided by 10 simplify to? Simply 2, and then e to the 0.05t. Now this will happen no matter what your principal is. If you put double the principal on the other side, so just say in general, if you have a equals a principal e to the rt, and you want to find the doubling time, then you would put 2p as your future value, twice the principal equals e to the rt. And if you divided both sides by p to cancel this out, then this would cancel as well on the left, and you would be left with 2 equals e to the rt. So that's just general when you're looking for doubling time. Also, whenever you're looking for half-life, that would be 1/2 equals e to the rt. So in some of these problems, you're actually asked to find the half-life, and some of them you're asked to find the doubling time. Now, you would be asked to find the doubling time if it's a growth question where you have a positive growth rate, and you would be asked to find the half-life if it was a decay problem where the growth rate was actually negative, right? So that's what we're going to do. We're going to set up what we have here. Just put a 2 and get rid of the p, and then solve for t. So remember, I'm still using the a equals whatever my principal is that I stored into variable c in my calculator times e, the natural number e, to the power of the growth rate that is stored in my b variable in my calculator, and then times t. So now, since I want to find doubling time, I will actually put 2 in place of a and get rid of the c, and then solve for t. So the next step then is to take the natural log of both sides. That way I can get the exponent down to ground level. So then I have natural log of 2 is equal to b times t. Because again, remember, the log base e of e simplified to 1, and that exponent was in front of the log. Then I can divide both sides by b to cancel this out and get t alone. So my my doubling time will be found by calculating natural log of 2 divided by b in my calculator. So that will give us this answer. All right, now find the population after 80 minutes. All we do is take our A equals C e to the bt, and we substitute in 85 minutes and then calculate that to get, oh, I'm sorry, it's 80 minutes for this example. Sorry, 80 minutes there. So I would plug in 80 minutes. And calculate that. And that would give me this answer here. And then when will the population reach 1400? When, right? So they're giving us the population of 14,000 rather, and asking us when. So in other words, here is the future value. Tell us the time that it'll take to reach it. So again, we're going to be solving for t. So we come back to this right here, right? And we replace the a with that future value of 14,000. And solve for t. So we will divide both sides by c, then take the natural log of both sides to cancel out the base of e, then divide both sides by b to cancel out the b and get t alone. So calculating the natural log of 14,000 divided by c, quantity divided by b, is going to give us that final answer here. So I hope that was helpful. I know the first part of it was very long and drawn out. That's one of the more difficult problems, and I hope this was helpful.